All right, so I guess welcome everybody to another meeting of the JAIA. So yeah, as I mentioned in the WhatsApp chat, for this meeting, I think we can maybe look at some recent developments that happened. Well, some recent stories that came up this week. Two main stories. Well, Jordan, you had posted one of those stories. So the first one was the thing. Let me actually just bring up my screen, bring up the actual story. All right, here's
Hold
one.
on.
Are you seeing one? Oh yeah, you are. Yeah. So this one. So this is Facebook. Um, says its new Instagram train. AI represents a big leap for computer vision. Um, in my opinion, I think a lot of these magazines and news agencies kind of like to over embellish like headlines to make it look way bigger than it actually was. So, when they say things like a big leap or, some great thing, when you actually read the paper or read the actual blog post from the actual research agency, then you realize it's a step, but not necessarily something huge. But yeah, this was a story. Basically saying that Facebook made some big step in computer vision. So I mean, I guess just reading the summary of the or what's here. So basically, they're saying Facebook created an artificial intelligence system that made it much more efficient for companies to train software for range of computer vision tasks, from facial recognition to function needs for self-driving cars. Um, so Jan LeCun, which is Facebook's AI chief, says here that so it can learn the way a human infant does through observation by building a mental model of relationships between objects. So the idea, I think I was reading the actual blog post from from Facebook's research. So it's called SEER, SEER, which stands for self-supervised. So the idea is that they're using self-supervised learning. The idea I get here is that they basically just fed kind of like how they train GPT-3 with like a bunch of text. They kind of did the same thing here, but with images. So they fed this model with a bunch of images, and basically through well, self-supervised learning, it basically learns. Um, think of it as the relationships between the images and the underlying abstract meaning. And from that, you can use it um, for zero-shot learning tasks. So I don't know if you guys saw this story, um, or I don't know if any of you have any comments on this particular story.
Yeah, well, I haven't gotten to read the actual
Mm-hmm.
blog post, or I'm not sure if there's a paper out on it, but I haven't gotten to read that either.
Yeah,
But
yeah.
like, how big is the model itself?
Yeah, so what I'm gonna do is basically just do like a quick run through of this or the blog post. So I'm not gonna read word for word, but just kind of pick out the major details. And I guess from there we can, I guess, talk about what we just read. So, say the whole idea is being able to solve the problem of needing huge labeled data sets to train computer vision models. So this is supposed to help with that problem. So some key things I pick out here, it's a billion parameter model. So it's saying it's a self-supervised computer vision model that can learn from any random group of images on the internet. without the need for careful curation and labeling that goes into most computer vision today. So it seems here it's trained on unlabeled and uncurated public Instagram images, and it outperformed state-of-the-art self-supervised system, reaching 84% top one accuracy on ImageNet. Um, it says here also it outperforms state-of-the-art supervised models and downstream tasks, including object detection, segmentation, image classification. When trained with just 10% of the examples in ImageNet dataset, SEER still achieves 77% top one accuracy on the full dataset. When trained with just 1% of the annotated ImageNet examples, SEER achieved 60.5%. I think that's pretty interesting that with just 10% of the examples on ImageNet, it still was able to achieve that high of an accuracy. I guess it comes back to the whole thing of where I see the field kind of moving towards zero shot learning. But let me see if there's anybody else that wants to come into the meeting. Participant. Okay. Yeah, the direction I see the field kind of moving towards the whole ability of learning new tasks pretty quickly. So the whole idea of basically training these big models with a lot of parameters on these unlabeled in sort of like an unsupervised fashion, and then from there you can use it for other tasks. So it's pretty interesting that with just 10% of the images in ImageNet, I think has about, is it a million? There's a lot of images. It still was able to achieve that much of an accuracy. So let's see here. So it says major breakthrough that clears the path for more flexible, accurate, and adaptive computer vision models. Let me scroll on more. So here they're comparing basically the difference between self-supervision for vision problems versus with text. So as I mentioned earlier, um, something similar was done with GPT-3 and text. So the idea is to do the same with images. But they're saying here the problem with text versus images with text, semantic concepts are broken up into discrete words. But with images, algorithm must decide which pixel belongs to which concept. So basically, they're saying there that it's easier to do this with text than it is with images. Because I mean, images are made up of pixels, and slight changes in brightness or values to one of those pixels is basically a whole well, it's basically can be a different image. Um, so here they're saying it required two key components: algorithm that could learn from a vast number of random images without any metadata or annotation, and a convnet large enough to capture and learn every visual concept from this large and complex data. Right? They say here it took advantage of a new algorithm called SWAV, which developed from SWAV uses online clustering to rapidly group images with similar visual concepts and leverage their similarities. Okay. So I think down here they give some more details. So you're saying some benefits of self-supervised learning can help specialize models in domains where we have limited images or metadata, like medical imaging. With no labor required upfront for labeling, models can be created and deployed quicker, enabling faster and more accurate. So this is, I guess, highlighting one of the drawbacks of supervised learning, which requires labeled data. So this is supposed to be a lot helpful in terms of being able to train new models instead of having to label data again and again for some new task that you're trying to accomplish. And you can basically just use this model that was trained on a bunch of data in a sort of unsupervised fashion to help with those downstream tasks, like maybe say image recognition for dogs or something like that. I think this actually, let me see, there's another post that gives more detail. Yes, this one that gives more detail on the actual architecture.
Well, quick question.
Yeah.
They said that they used another architecture called
Mm-hmm.
Suave. So I wasn't sure, like I wasn't like completely clear on that part. So they were basically saying that Suave is like the feature extractor of the network.
Yeah, yeah, yeah. So this is what I was saying. The article, well, the blog post I just clicked on, I think should give us more details. In fact, let me just open this thing. But yeah, I imagine that Suave would be the feature extractor. Um, where is contrasting? So the abstract here says unsupervised image. Yeah, so the blog post, this one, I think gives more detail on the actual feature extractor, like how it was trained and stuff like that. I think it used something called a contrastive loss, which I've been hearing a lot about lately. So hopefully this can give us more details as to exactly what's happening. Sorry, so let's see if we can do a read of this. So yeah, this first part, this here, they're just talking about the same thing I was mentioning about supervised learning and disadvantages with requiring massive amounts of labeled data. Um, so here they're saying as babies, we learn how the world works largely by observation, form generalized predictive models about objects in the world by learning concepts such as object permanence and gravity. So I guess in a way they're trying to allow the model to learn some sort of common sense rules or relationships between different objects that it sees. So I guess it's sort of kind of moving the field away from just this brute force associative sort of thing where you have an image it's associated with a label to more something that seems more intuitive and logical. Different objects in a scene has different relationships, and you can use that to, I guess, get a better meaning of what you're actually seeing. So let me scroll down. All right, so you're saying self-supervised. So here you're saying we believe that self-supervised learning is one of the most promising ways to build such background knowledge and approximate a form of common sense in AI systems. Self-supervised learning enables AI systems to learn from orders of magnitude more data, which is important to recognize and understand patterns of more subtle, less common representations of work. So here they're saying basically self-supervised learning has had success with NLP. So they mentioned models like BERT, and GPT-3 is kind of like BERT. Um, so their latest research project SEER, which we were just reading about, leverages SWAB and other methods to pre-train a large network on a billion random unlabeled images. A billion, wow. Random unlabeled images, yielding top accuracy on a diverse set of vision tasks. That's interesting, a billion. That's the thing, I guess the only drawback with a lot of these new developments. I think with the last model, or one of those models I was seeing, like it required 256 GPUs to train it. And unless you're in like the US or Europe, it's highly unlikely you'll be able to get access to such resources, which I guess does open up some opportunity for people that are not in those countries to find more efficient ways to train these things. I mean, if you imagine, well, if you look at the brain, it's a lot more efficient than the whatever, well, our computer systems today. So I mean, let's say, for example, the brain can do a certain amount of calculations per second in terms of the amount of energy the brain uses versus how much energy it would require to do the same number of calculations per second on, say, a supercomputer. There's a big difference. So, you know, there must be a reason, or there must be a reason why the brain is a lot more efficient than, say, our modern day computers. There's some research into this, like neuromorphic hardware, so chips that kind of resemble more neurons in our brain. Yeah. So it's saying here self-supervised learning obtains supervisory signals from the data itself, often leveraging the underlying structure in the data. The technique of self-supervised learning is to predict any unobserved or hidden part of the input from any observed or unhidden part. Okay. For example, as it's coming in LP, we can hide part of a sentence and predict the hidden words from the remaining words. Okay, that makes sense. You start off with like a few words of a sentence and you can predict the next words. And you can also predict past or future frames in a video from current ones. You can make use of a variety of supervisor signals across co-occurring modalities and across large data sets. Yeah, so here they're explaining difficulty of language versus vision. So he said the models are pre-trained in a self-supervised phase and then fine-tuned um, for a particular task, such as classifying the topic of a text. So the system is showing a short text in which some of the words have been masked or replaced. The system is trying to predict the words that were masked or replaced. So I think the gist of this paragraph is saying basically predicting what's missing from text is all a much easier task than doing the same for images. So they're saying these techniques, however, can't be easily extended to new domains such as computer vision. Despite promising early results, SSL has not yet brought about the same improvements in computer vision that we have seen in NLP. And saying here, the reason for that is that it's considered more difficult to represent uncertainty in the prediction for images than it is for words. When a missing word cannot be predicted exactly, the system can associate a score of probability to all possible words in the vocabulary and low scores for all other words in the vocabulary. So here they're saying training models at scale requires a model architecture that is efficient in terms of both runtime and memory. They mention here using a model family called RegNets. I don't know much about this. But it's saying here RegNet models are convenient, capable of scaling to billions or potentially even trillions of parameters and can be optimized. So it does seem that the field is definitely moving towards these very huge, big models with, billions, even trillions of parameters. Um, GPT-3, I think, had about 175 billion. So definitely direction seems to be towards these large, big models that are trained in sort of an unsupervised slash self-supervised fashion on a lot of data. And then those models can then be used in downstream tasks later on. All right, so here, there, I think they're going to be talking more about the SWAB thing that we saw earlier. So new techniques, SSL, such as SWAB, are starting to beat accuracy records in vision tasks. This is best demonstrated by a SEER system that uses a large convolutional network trained with billions of examples. So here they're saying with NLP, predicting missing words basically involves computing a score of what's basically but here they're saying CV on the other hand, another starts of predicting missing frames in a video, missing patches in an image, or missing segment in a speech signal involves a prediction of high dimensional continuous objects rather than discrete outcomes. So there are an infinite number of possible video frames that can plausibly follow a given video clip. It is not possible to explicitly represent all the possible video frames and associate a prediction score to them. In fact, we may never have techniques to represent suitable probability distributions over high dimensional continuous spaces, such as a set of all possible video. That basically what they're saying here. Usually for like NLP tasks, when you're predicting the next word, usually you have like a fixed vocabulary of words, and then basically they using something like a softmax, they produces sort of like a normalized probability distribution of what's the likely or the most likely word to follow. But with something like images where data is not fixed or discrete, it's more continuous and high dimensional, it's basically intractable to do the same thing. So here I think they're giving more details on, what exactly the model entails. So here they're saying they're using an energy-based model. They say energy-based model, a trainable system that given two inputs, X and Y, tells us how incompatible they are with each other. For example, X could be a short video clip, Y another proposed video clip. Machine would tell us to what extent Y is a good continuation for X, indicate incompatibility between X and Y. The machine produces a single number called an energy. The energy is low, X and Y are deemed compatible, but if it is high, they are deemed incompatible. Okay. Um, so training an EBM consists of two parts, showing it examples of X and Y that are compatible and training to produce a low energy. And two, finding a way to ensure that for a particular X, the Y values that are incompatible with X produce a higher energy than the Y values that are compatible with X. So they say part one is simple, but part two is where the difficulty lies. Let's see why. For image recognition, our model takes two images, X and Y, as inputs. If X and Y are slightly distorted versions of the same image, the model is trained to produce a low energy on its output. For example, X could be a photo of a car, Y a photo of the same car that was taken from a slightly different location, different time of day. So the car in Y is shifted, rotated, larger, small, and displaying slightly. So they're, I guess, giving an architecture as to what could achieve this. Something called a Siamese network. From what I remember, with Siamese network basically takes in two inputs, produces an embedding, so it's a vector representation of the two inputs, and then some comparison is done between. So here they say networks produce output vectors called embeddings, which represents X and Y. Third module joining networks at the head computes the energy as the distance between the two embedding vectors. When the model is shown distorted version of the same image, the parameters of the network can easily be adjusted so that their outputs move closer together. This will ensure that the network will produce nearly identical representations of an object regardless of the particular view of the object. It seems here how they're training the model is by allowing it to learn what images are basically the same or compatible, and to essentially form some representation of that, and to do the opposite as well, learn which images are completely different and have some sort of hidden representation of that. And you're seeing here difficulties to make sure the networks produce high energy, different embedding vectors when X and Y are different images. So a specific way to do so, two networks could happily ignore their inputs and always produce identical output embeddings. This phenomenon is called a collapse. When a collapse occurs, the energy is not higher for non-matching X and Y than it is for matching X and Y. Okay. So I guess they're just giving some techniques to avoid. So here, contrastive. This says contrastive methods are based on the simple idea of constructing pairs of X and Y that are not compatible and adjusting the parameters of the model so that the corresponding output energy is large. Mhm. So here they're saying the method used to train NLP systems by masking or substituting some input words belongs to the category of contrastive methods, but they don't use a joint embedding architecture. Instead, they use a predictive architecture in which a model directly produces a prediction for Y. One starts a complete segment of text Y, then corrupts it by masking some words to produce observation X. Corrupted input is fed to a large neural network that is trained to reproduce the original text Y. An uncorrupted text will be reconstructed as itself, while a corrupted text will be reconstructed as an uncorrupted version of itself. If one interprets the reconstruction error as an energy, it will have the desired property low energy for clean text, higher energy. All right. So I mean, the gist I get from that is basically you have a corrupted input, and basically they're trying to reconstruct the original input, and that reconstruction error is used as energy. Um, let's see if they see anything about it. They're saying we cannot use this trick for images because we cannot enumerate all possible images. And we touched on this earlier. Is there a solution to this problem? Short answer is no. There are interesting ideas in this direction, but they have not yet led to results that are as good as joint embedding architectures. So this seems like an interesting area of research or further research. One interesting avenue is latent variable predictive architectures. And they're giving some details on that, saying latent variable predictive models contain an extra input Z. It's called latent because its value is never observed. So latent variable models can be trained with contrastive methods. A good example of this is a generative adversarial network. Critic can be seen as computing an energy indicating whether the input Y looks good. The generator network is trained to produce contrastive samples to which a critic is trained to associate high energy. But you're saying contrastive methods have a major issue. They're very inefficient to train. High dimensional spaces such as images. There are many ways one image can be different from another. All right. And I think the last technique here is a non-contrastive energy-based SSL. Non-contrastive methods applied to joint embedding is possibly the hottest topic in self-supervised learning at the moment. So non-contrastive methods to joint embedding include a lot of these models here. So they say they use various tricks such as computing virtual target embedding subgroups of similar images, or making the two joint embedding architectures slightly different through the architecture or the parameter vector. Yeah, so this is definitely something um, you would have to look more into. Yeah. All right, so that's I think as much as I'll go through with this particular thing. But I mean, the general idea I get is that essentially what they did with GPT-3, which was basically in an unsupervised fashion, um, just feed it a lot of text, um, and then train it to predict the next likely word. So they're trying to do the same thing with images, but as you see, the difficulties with text versus images. With a text, they have a fixed vocabulary, so it's easy for it to just compute like scores for the next likely word. But for images where the input is high dimensional, continuous data, it's a lot harder to see how that would be done. Um, so basically, you know, their model SEER, which they, I guess, trained in a self-supervised fashion, was able to be used on some downstream tasks like image recognition on the ImageNet dataset, which achieved, I think, just using 10% of the data, up to 74% accuracy. So yeah. All right. I mean, do you guys have any thoughts on maybe what we read a while ago? I mean, I know it's probably a lot to take in, since you probably would need to like maybe read the actual paper, kind of do some more deep dive into actually how it works. But in the general gist of where you see the field moving, where they're essentially training these large models and a lot of data. Do you think this is a suitable direction towards, you know, maybe in the future, AGI systems, training these
Um,
large high parameter models?
oh yeah, well, I think that is a good step forward. I was reading an article the other day that said, um, like that said, it was talking about how humans actually learn.
Yeah.
And like now that after the first like year or so of your life, you've already learned, well, for visual tasks, you've already learned how to like identify
Yeah.
people basically. So you can do those things like zero shot, but initially in the first year of your life, um, where you for the first couple months or so, like although you'd be able to identify like your mother, for example, you wouldn't be able to identify consistently other people that are coming around to you. So
Mm.
they were basically saying that um, it does take it does take humans a while to build up that intuition that we use for the rest of our lives. So I think that um, training models like this is a similar-ish process,
Mm-hmm.
like they where the models are like they can just learn how to just learn the intuition for how to identify various things, how to understand the semantics and the geometry of a scene and those
Yeah.
kind of stuff, and then apply that to different tasks.
Mm-hmm. All right. Yeah, I agree. Um, yeah. I mean, I mean, it's something that I've always been like, thinking about, you know, moving from these, as I said earlier, models that essentially just kind of like associative learning, where you just have this image and you kind of fit it to a label, to more, you know, compositional relational models that can understand, relation between different objects and, you know, you know, how they match together in the scene and stuff like that. I think it's definitely important that we move towards that sort of or those sort of models, I should say. It's definitely a lot closer to how humans think. All right. Who else is here? Anybody else have any more thoughts on this particular article? Right. All right. So what we're going to do now is just move on quickly to the next article, which I think is the more interesting one. I think you had shared this one, Jordan. Let me see. Yeah, this. Let me see here. Try moving. Yeah, this thing released by OpenAI. So basically, this came from Clip. So I guess probably I should quickly look at Clip first, and then go over to what happened here. Um, so yeah, so basically, Clip connecting text and images. So let's kind of see what first of all what Clip is, and then we can talk about what um the interesting result they found here. So basically, it's kind of along the same lines of training these large models in a sort of unsupervised fashion. So it says present a neural network um, that aims to address these problems, trained on a wide variety of images, wide variety of natural language supervision. And it says network can be instructed in natural language. Well, no. All right. The I think is saying less than a minute. So this particular meeting is gonna end soon, but when it comes off, just I think you can just click back on the link. And you just rejoin. They're saying less than a minute. Yeah, whenever like you stop hearing or the Zoom meeting cuts off, just click back on the link and you should be there. So yeah, what's it saying now? So basically it's saying the network can be instructed in natural language to perform a great variety of classification benchmarks without directly optimizing for the benchmark's performance. It comes out the same zero-shot learning that you saw in things like GPT-2 and GPT-3. All right, so what exactly is this thing doing? So they're talking about zero-shot learning here. They're saying a critical insight was to leverage natural language as a flexible prediction space to enable generalization and transfer. So they're saying here, most inspirational for CLIP is the work of Ang Lee and his co-authors at FAIR who in 2016 demonstrated using natural language supervision to enable zero-shot transfer to several existing computer vision classification datasets, such as the ImageNet dataset. So they achieve this by fine-tuning an ImageNet CNN to predict a much wider set of visual concepts from the text of titles, descriptions, and tags of 30 million click-up photos. All right, so the important part here, though. So, Rosa. Yeah, so the approach, you say saying we should scaling a simple pre-training task is sufficient to achieve competitive zero-shot performance in a great variety of image classification datasets. So our method uses an abundantly available source of supervision, the text paired with images found across internet. Okay. They're using two things, text and images to train the thing. So they're saying given an image, predict which out of a set of 32,768 randomly sampled text snippets was actually paired with it in our dataset. So given an image, predict which text snippet is paired with. So it's saying here, intuitions that clip models will need to learn to recognize a wide variety of visual concepts in images and associate them with their names. As a result, clip models can then be applied to nearly arbitrary visual classification tasks. For instance, if the task of a dataset is classifying photos of dogs versus cats, we check for each image whether a clip model predicts the text description, photo of a dog or a photo of a cat is most likely to be paired with. So it seems here they have something to encode the text in some vector representation. Same thing with the images. And I guess it's the same thing where they're comparing, they're not comparing, or the loss function is to see which image match up with which text. So I'm guessing this network or whatever is learning some hidden representation based on this. And I guess they can use this for downstream tasks like image captioning. So I think this really comes back to the same thing we were reading a while ago with the Facebook model. They're saying CLIP was designed to mitigate a number of major problems in the standard deep learning approach, computer vision. The costly data sets, image data set, require 25,000 workers, 40 million images. CLIP learns from text image pairs that are already publicly available on internet, reducing the need for expensive, large label data sets that have been extensively studied. ImageNet model is good at predicting the 1,000 ImageNet categories, but all it can do is that out of the box. So basically, they're comparing CLIP to a regular ImageNet model. And they're saying CLIP can be adapted to perform a wide variety of visual classification tasks without needing additional training examples. So it comes back to the whole thing where we see the field moving towards zero-shot models, which should make systems that are more adaptable and robust. And it says to apply clip to a new task, all we need to do is tell clips text encoded the names of the task visual concept that will output a linear classifier clips visual representation. They're giving some examples here. So you say something like you have this picture here and it's saying photo of guacamole. I have a picture of a television studio. This is some pretty impressive results. It seems, yeah, given an image, it can in text tell what it's about. So key takeaways: clip is highly efficient, learns from unfiltered, high noisy data. Um, so basically, you're just talking about the architecture that they use. So I guess the image embedding. Let me see. Like this comes back contrast, and I see this a lot in a lot of new papers. Contrastive objective used by clip is 4x 10x more efficient at zero-shot imaging classification. Second choice is adoption of the vision transform, which gave us a further 3x gain in compute efficiency. And yeah, it was trained on 256 GPUs for 2 weeks. Can you imagine how much money that's gonna be? But you're saying here, importantly, clip is fixed, flexible, and general. Um, so it says we have measured clip zero-shot performance on over 30 different data sets, including tasks such as fine grain, object classification, geolocalization, action recognition in videos, and OCR. But some limitation, it says clip usually performs well on recognizing common object. It struggles on more abstract or systematic tasks, such as counting the number of objects in an image. On these two data sets, zero-shot clip is only slightly better than random guessing. Zero-shot clip also struggles compared to task-specific models on very fine-grained classification, such as telling the difference between car models, variants of aircraft. It says clip also still has poor generalization to images not covered in its pre-training dataset. For instance, clip learns a capable OCR system when evaluating hand-reaching digits. Zero-shot clip only achieves 88% accuracy, well below the 99% of human data. It says here clip allows people to design their own classifiers and removes the need for task-specific training data. The manner in which these classes are designed can heavily influence both model performance and model bias. For example, we find that when given a set of labels including fair face, race labels, and a handful of egregious terms such as criminal, animal, model tends to classify images of people ages 0 to 20 in the egregious category at a rate of 32%. I think this is a common theme in a lot of these models. And it's something that's been talked a lot lately. You know, the biases in a lot of these systems. I mean, given that the fact that you're basically just using uncurated data, raw data straight off the internet, then you are going to expect that a lot of your data will have some, well, will have some inherent bias with it as well. All right, so um, that's clip. Now the interesting result that came out of this is this. They're saying multimodal neurons in artificial neural net. So it says we've discovered neurons in clip that respond to the same concept whether they're presented literally, symbolically, or conceptually. This may explain clip's accuracy in classifying supervising visual renditions of concept, and is also an important step toward understanding. So let me, I guess, down here we'll explain what it means by that. essentially, basically, and it is, I think, a very cool thing because and I think Jordan, you had asked me this earlier or recently about the whole thing about multimodal learning and being able to do both vision and processing text at the same time. And what I find cool about this is that you can show this thing a picture of Halle Berry, a sketch of Halle Berry, and the name Halle Berry, and the model is able to associate all of those things with Halle Berry. The same thing here with a picture of Spider-Man, a sketch of Spider-Man, and text with Spider-Man, and I can associate all those things with Spider-Man. So I mean, somehow it's able to understand a concept in different modalities: image, a sketch, a text, so on and so forth. So here they're saying they're releasing a discovered presence of multimodal neurons. One such neuron, for example, is a Spider-Man neuron. Um, a response to an image of a spider and an image of the text spider and the comic book character Spider-Man, either in custom or illustrated. It says our discovery of multimodal neurons in clip gives us a clue as to what may be a common mechanism for both synthetic and natural vision system abstraction. We discovered that the highest layers of clip organize images as a loose semantic collection of ideas, providing a simple explanation for both the model's versatility and representations compactness. Um, so they say neurons appear to be extreme examples of multifaceted neurons, neurons that respond to multiple distinct cases only at a higher level of abstraction. So I found this cool as well. Um, so they were able to, somehow visualize the activations, um, or they interpret somewhat what the neurons inside this model, basically how it represented the data. And just seeing these visual representations of that is pretty fascinating. Like we'll have summer here, we'll have winter. So I mean, one of those the criticisms of these black box model is the whole thing about not being interpretable, or you're not or not being able to understand exactly why it made certain decisions. But it does seem with these new advancements, we're getting closer and closer to more interpretable models. I mean, even looking at these, it's pretty, I mean, look at this shot. These, I mean, it's weird like how it represents it, but it's I don't know. It's almost like a dream world representation. And I mean, if you think about it, we as humans we dream as well. And I mean, there has been studies that shown that dreaming actually allows us to um, organize concepts in the brain. So yeah, those are some examples. This says we were surprised to find many of these patterns appear to mirror neurons in the medial temporal lobe, documenting epilepsy patients with yeah, so some neuroscience stuff. Um, So it says, while this analysis shows a great breadth of concepts, a simple analysis of neural network cannot represent a complete documentation of model behavior. The authors of CLIP have demonstrated, for example, that the model is capable of very precise geolocation with a granularity that extends down to the level of a city, even a neighborhood. In fact, we offer an anecdote. We have noticed by running our own personal photos to CLIP that CLIP can often recognize if a photo is taken in San Francisco and sometimes even a neighborhood. That's pretty interesting. Um, Bennett. Oh, I'm reading the chat. Bennett says he's running an ML algorithm or GAN, generate synthetic images of objects. I saw your post on that, the crypto art. Um, what's that all about? You're selling artwork made by GANs and people pay for them using cryptocurrency? Okay, all right. So, I mean, have you produced, well, I guess you have, oh, risky business. Yeah, I imagine so. So, I mean, have you had any sales? Has anybody taken you up on your artwork? Or has it actually produced any, or in your opinion, good looking artwork? Oh, so far no sales yet. No artwork has been generated by GANs yet. Okay. All right. Would love to hear more about that, or how you train the gun sometime. All right, getting back to this now. So it says these multimodal neurons can give us insight into understanding how clip performs classification. So I guess they're doing some interesting things here. So they combining finance. This is kind of like the word to vector representation. Like when they do some vector operations on them, like you have something like king, um, what is it? Uh, yeah, something like king minus woman, and get something like queen or something like that. Yeah, I guess something like this. Yeah, finance plus dolls, piggy bank, Spider-Man animal. Yeah, so here it's saying the same thing I was basically saying. So a key observation that these concepts are contained within neurons in a way that's similar to the word-to-vec objective. Concept therefore from a simple algebra that behaves similar to a linear proof. So I guess you can do these linear operations to get these concepts. Surprise, you have celebration, hug, shock, smile, grin. So this is an interesting part of the article, and it comes back to why I think self-driving cars, there's some potential dangers with that. The whole thing with adversarial attacks. It says degree of abstraction in clip surfaces a new vector of attack that we believe has not manifested in previous systems. Like many deep networks, representation at the highest levels of the model are completely dominated by such high-level abstraction. What distinguishes clip, however, is a matter of degree. Clip's multimodal neurons generalize across the literal and the iconic, which may be a double-edged sword. There are a series of carefully constructed experiments which demonstrate we can exploit this reductive behavior to fool the model into making absurd classifications. They will observe that the excitations of the neuron in clip are often controlled by its response to images of text, providing a simple vector of attack in the model. So the finance neuron, for example, responds to images of piggy banks, but also responds to the string dollar sign, dollar sign, dollar sign. By forcing the finance neuron to fire, we can fool our model into classifying a dog as a piggy bank. So I find this pretty interesting. They put like some dollar signs on this thing here, and it misclassified this thing as a piggy bank. And this one I also found interesting. So basically they write iPod so on a piece of paper and put it in front of the Apple, and the model now sees it as an iPod, even though it's not actually an iPod. But it's kind of weird because maybe in a sense it's like it's just reading what it sees. I mean, it sees iPod, so that's what it's saying. It sees an iPod, but um, it's not really an iPod. But it's interesting that just putting piece of paper on the Apple with iPod, you know, says it's an iPod. So yeah, basically it just goes on to talk about some different biases and just give a conclusion. But I think the main idea of this paper is that, you know, it comes back to the whole thing about um, moving toward less about supervised learning, where we have or solving the deficiencies of supervised learning, where we have these large um, data sets that have to be hand labeled by humans, which is a big drawback to supervised learning in general. It basically requires a human in the loop. I'm seeing where these systems are requiring less and less humans in the loop. So they're basically learning under in a sort of like an unsupervised fashion. And with this, they're found out that they're by interpreting the representations of different neurons in this model, that it's able to somehow form multimodal representations of different concepts. So like something like Halle-Berry, it can, whether it's a text, whether it's just a sketch, or whether it's an actual image of Halle-Berry, it still is able to represent all that as Halle-Berry, which basically is moving towards systems that can both see, and read, because I mean, if you're gonna build an AGI system, it should be able to learn. So it should be able to maybe just think of it creating like a robot, should be able to maybe pick up a book and read it. That I think it's some pretty interesting results. Any thoughts on this, Jordan? I mean, I think you read you said you read the article. I mean, you said it was a big step towards AGI. Why do you say?
Oh well, I was thinking along similar lines as you,
Mm-hmm.
where um through AGI system should be able to understand, well, associate um visual and textual concepts, and the fact that this um allows the same neurons to fire for both of those concepts, like shows that it is attaching the same, so that it's like understanding the similarity between the concept in the different modalities.
Yeah, I agree. Let me check the chat. Uh, okay. Yeah, I agree. Definitely this it's definitely showing some interesting results. But I definitely always take these things with a grain of salt. This is why I usually like to kind of go deeper into the parts where they say it has deficiencies. So for example, the attacks that they said could happen, where you put the dollar sign on the dog and it sees it as a piggy bank or whatever. Yeah, so I mean, this definitely still shows that we are still far away from systems that really understand or have true image understanding. Because I mean, if it did have true image understanding, then it shouldn't have fooled that. To us humans, we can easily look at that and see that it's a dog, but it's just covered with some dollar signs. But to this model that's trained, it's clearly fooled easily, which is why I've been always pretty conservative on the efficacy of self-driving cars coming up, because I mean a lot of these are built, their perception models are built on these neural networks, and I mean until, in my opinion, we have true image understanding or models that have true image understanding. Um, and there are going to be scenarios. It might work like 98% of the time, but there are those 2% scenarios where, say, for example, the car um, just rams into some pedestrian, you know, and it was clear that the pedestrian was out in the middle of the road. So why didn't it stop? But it just didn't stop. And we've seen an example of this with Uber's, not Uber, yeah, Uber's self-driving car. Um, so yeah, so I mean things like that could literally halt self-driving production. Um, so I mean, in my opinion, although they say statistically it should lead to less deaths, it's still a more complicated issue because if a self-driving car kills someone, who gets the blame? Who gets sued? Is it the person in the car? Is it the car itself? The company. Of course, companies have their legal protections and all that stuff. But it definitely gets into some kind of gray water. And you also have things like the trolley problem, whether to save the passengers in the vehicle or prioritize um, pedestrians on the road. Which one do you save, or whose life do you prioritize? These are all ethical questions that we still need to be discussed or answered in the AI community. All right, let's 10:10. I think we've covered most of what we wanted to talk about today. It was a pretty good paper reader. Um, so yeah, I mean we can do more of this. Like, feel free guys to, if you see any new articles, new blog posts, new papers that maybe you've read, it seems pretty, or you find it pretty interesting, or maybe there's some math in there you don't quite understand, and maybe we can go through it together so you can better understand it. And feel free to let us know, and we can have meetings like this where we kind of dig deeper into the models, try to understand the math, so that we can make systems like this. Yeah.
Oh, speaking of that, speaking of that,
Mm-hmm.
there was another article that I read that I
Yeah.
forgot to send in the group. So
Mm-hmm.
I mean, I guess I can send it in there now, and we'll probably talk about it another time,
Yeah.
or because I'm not sure how much here.
All right. We can do it. What's it about though? If you remember. You hearing me? You remember what's it about? Or what the
Yeah,
article,
yeah.
the main gist of the article?
It was I just sent it in there. It's about
Oh,
reinforcement learning approach to self-driving cars.
oh, okay. All
Yeah,
right.
and
Oh,
but
this seems
um,
interesting.
yeah, basically what the gist is that um like when we dream, we a lot of the times we've never actually seen the things that we dreamed about before. So our minds basically extrapolate on our previous experiences to simulate experiences. So they're saying that if you could um, use a similar concept to train a machine learning system, then I think what it was basically saying was that it could drastically reduce the amount of data that it takes to train a system like that.
Yeah. Yeah, I agree. I mean, I've seen several RL models that kind of work on the same concept of imagination, kind of simulated reality, building sort of like a world model, and then as you say, extrapolating on that to like new scenarios and stuff like that. Yeah, definitely, it's the way to go. Um, or yeah, I mean, I think that's a definitely interesting direction for research. The whole idea of imagination and dreaming, and how big of a role that plays in learning as humans. That is definitely an interesting research direction. So yeah, I mean, I definitely take a look at the link that you sent. and maybe we can even discuss it next week for sure. All right. Before I go though, so I sent out a link for anybody that wants to do like a presentation at the upcoming kind of conference thingy that we're planning to do. So I mean the whole idea, I mean it's nothing fancy or anything. It's just, if you're doing something in AI, whether it's just a project or if you're doing research, or if it's just something you did recently, like some new technique, or even it doesn't even have to be new, but it could literally just be a tutorial on how to do X. Feel free to sign up on the forum. The whole idea is to get you guys some exposure. Hopefully, maybe even somebody international can view these things, and then that can help you with your own career in the field of AI. So I'd encourage you guys to sign up. It could be a simple tutorial on like how to train an image classifier, something simple like that. Just to showcase what you know. So yeah, that's my piece of advice there. Of course, more details about what this actual quote unquote conference is gonna look like. Obviously, it's probably gonna be something with like Zoom or some online platform, because COVID is still a thing. So yeah. All right, guys. I think that's it. Thanks for coming out. I'll see you next week, if anything. All right, bye, guys.